Hi, my name is Corey Cianello, and this is Lab 4 of Physics 2212. In this lab, I analyzed the motion of a magnet falling through a tube of aluminum foil. The tube acts very similarly to a line of wire rings, each being the same diameter and thickness. We learned that for a single ring, a moving magnet induces a current in it. This causes the ring to behave like a second magnet with its own dipole moment and magnetic force that acts on the moving magnet. The goal of this lab was to analyze how these forces from a tube of aluminum foil affect the motion of a falling magnet. These are the governing equations that I used. The first is the calculation for the magnetic field of the falling magnet. R is the distance from the bottom tip of the magnet to the edge of the loop, and mu is the magnetic moment. The next equation is Faraday's law. It states that the time rate of change of the magnetic flux is equal to the EMF of the ring. For this experiment, it can be found using this equation, where mu naught is a constant, y is the vertical distance between the magnet and the ring, and rho is the radius of the ring. The third equation is Ohm's law, which states that the EMF divided by the resistance of the ring is equal to the induced current. Finally, the magnetic force on the loop can be found from Newton's third law. The magnitude of this is the same as the magnitude of the magnetic force by the loop on the moving magnet. They act in opposite directions, with F on loop acting down and F on magnet acting up. Here is my data from the tests. I dropped the magnet from rest through a tube of aluminum foil. I held the tube suspended in the air so that the magnet could pass all the way through. I repeated the experiment 5 times so that I could minimize error in my analysis. These are the times that I measured from when the bottom of the magnet entered the tube until the top end exited. The average time was 2.19 seconds. During the experiment, I observed visually that the magnet slowed down inside of the tube and that it traveled at the same speed until it exited. The magnet also turned to an angle so that its top and bottom edges were against the sides of the tube. Here is a glow script model of the experiment. The aluminum foil tube was modeled as a line of wire rings. The video is sped up. As you can see, the time it took for the magnet to fall through the tube in the model was 10 seconds, about 5 times longer than what was observed. This does not make sense as the foil was only 31 centimeters long. I believe there was an error somewhere in my code, however, I could not figure it out. What if? What if the foil's resistivity was reduced to as close to 0 as possible? The resistance appears in the denominator of Ohm's law. When this denominator gets closer and closer to 0, the current gets larger and larger, closer to infinity. When we plug infinity into the magnetic force equation, and the force becomes infinite, meaning that the magnet would be pushed upwards and never fall through the tube. What if holes or slots were cut into the tube? Then there would be gaps in the rings. They would not be complete circles, meaning that my model would not be accurate. In conclusion, I proved that induced currents in a wire loop produce a magnetic force. This force has the same magnitude as the force on the loop by the magnet. I observed this interaction between a bar magnet and a roll of aluminum foil, which acts like a line of wire loops. The magnet slowed down inside of the foil and traveled at a constant speed. This shows that the force acts upwards, opposing the direction of the magnitude's motion, as well as gravity. That is all. Thank you.